Hello, my name is Finnegan Wilson.
I'm Daniel Azbell.
Acosta.
Josh Gallaher.
And today we're going to present on some non-standard fracture behavior of a S17-400 stainless steel alloy.
A large billet of 17-4 was sent to LNL for testing, and they pulled out samples at various locations, longitudinally through the billet, radially out from the center, and tangentially to the neutral axis of the billet. So, this is the manufacturer's sheet that was provided with the billet. We can see that the chemical composition of the billet falls entirely within the ASTM standard for this type of steel, which is referred to as type 630 by ASTM. The only difference is the sheet calls out columbium and tantalum. Columbium is an old name for niobium, and it uses a combination of columbium and tantalum to meet the standard's niobium requirement. This is acceptable as per a footnote under the 2019 version of the standard. So, also provided are the expected characteristics of this material in the H900 heat treat state. 17-4 is typically provided in what's known as the condition A precipitation and yield state. So this is where the material has sat in solution for a sufficient amount of time to reach an equilibrium temperature of 1900 degrees across the billet and then cool. It can then be overaged to various heat treat conditions by holding it at different temperatures. Those conditions are named for their temperatures, and H900 at 900 degrees Fahrenheit is the most common one. The properties provided are slightly higher than typical H900 properties, but do meet the minimum requirements of the standard. The trouble with using the material in condition A, it's softer that way, so easier to machine, so typically it's provided in that condition and then expected to be treated to H900. It can't be used in condition A typically because uneven precipitation during that long heat up and slow cool process can cause irregularities throughout the billet that can lead to unexpected brittle fracture, as well as varying yield strengths that can lead to unexpected ductile rupture.
So this type of steel is named for its ability to be precipitation hardened. Precipitation hardening is a phenomenon that takes advantage of the complex chemical composition of the steel. As the steel is initially going through its solution annealing process, we see the steel structure turn into something called martensite. That martensite is able to keep little packets of copper embedded within its matrix, which, as the copper accumulates, can help micro-strain harden the material. Additionally, as we go for the secondary heat treat, we're going to get some phase transitions of some grains of the martensite into the other form of steel called austenite. As that transition occurs, we're going to get a precipitation of a lot of these extra materials that are soluble in the martensite, but not so much in the austenite. And you'll get an accumulation of the niobium and the chromium carbide at the grain boundaries of the austenite. Now this can of course be overdone, but if it's done just right and you get a nice amount of micro strain around your grains, you can achieve an increase in tensile strength and a decrease in material ductility. However, if we compare then the solution annealed, or material A, with this long line up here, which is a short heat treatment time, versus this line that's a little bit lower over here, which is a longer heat treatment time, we can see that the different amounts of heat treatments, which then result in different amounts of precipitation, are going to heavily control the final strength and fracture properties of the material.
So we received 26 of these specimens from an outside manufacturer who did the machining. We have a double-ended threaded cylindrical specimen. Standard dimension is a 1/2 inch diameter. You can see this one here in particular exhibited some more brittle failure, abnormal for what we would have expected to see with this specific heat treat of material. So following all 26 tests, we decided to get a better look at what the microstructure looked like to better understand why we might be seeing more brittle failure versus ductile for these tests. So of the 26 tested, we opted to isolate 12 that exhibited some odd failure behavior. If you can see this graph here, it's pretty evident Here's our layout of specimens that were tested. The 2.5, which is closest to the center of the billet, tracks to about 2% elongation here versus the most exterior of that 15-inch diameter billet was the 13.9 specimen, which we see similar yield trends, but much more elongation, about 6 times more. Let's see. Working from the center outwards of the billet, we do kind of see similar trends of elongation, but there are some outliers that failed pretty unpredictably. So getting to look at the microstructure and see how the precipitation distribution varied throughout the billet was, we hoped would be revealing. And it actually did show us that we have more, we do have a notable distribution, but it is evident in our stress strain data that the elongation properties of this material could probably be tied back to the precipitate distribution.
From those results and SEM imaging, we can observe the microstructure and get a better idea of what the actual failure mechanisms were inside of these materials. Shown up here is just two standard, this is a brittle cleavage, and this is our typical cup and cone ductile failure. And then moving from left to right, we have the 2.5 radial sample, the 8.5 radial sample, and then the 13.9 diameter, is not really radial, whatever, radial sample. In the 2.5 and the 13, we saw very low levels of precipitation, leading to a much shorter elongation and more prone to these ductile and then ductile brittle mixed mode failures. Whereas in this 8.5, we see very high levels of precipitation with a ductile region, a very clear brittle cleavage region, and then another ductile region underneath it. Using this data and the results from prior, we believe that this material didn't actually ever reach its H900 heat treatment state. We believe that this is still in a condition A state, where that's right after the solution heat treatment. I believe for this was 1900 Fahrenheit for 8.5 hours. And in this state, the reason we believe this is it is prone to variety of fracture and unpredictability in the precipitate location and methods of failure. Because this material we believe is in condition A, we do not recommend using this for any sort of industrial applications or structural components, just because of the unpredictability of this material in failure.
We recommend that the material should be formally heat treated to its H900 state. Tensile tests should be done after this heat treatment to ensure that we've correctly reached the H900 state, and no structural application should be used for this material until it's reached its proper H900 state. Thank you for watching our presentation. Please be nice in the comments.